So Zoe, if you wouldn't mind double checking that it has audio and video, that'd be great. All right, folks, sorry for a 5-minute delay there. I had to give a talk on the other side of campus, and then I sprinted here, and now I'm very sweaty. So today we're going to talk about rendering. Before we get started, let's see, in terms of course announcements, I think all of our announcements are basically the same each time, which is that you continue to have homework. The mic dropped. Is this mic? Oy vey. Pay enough. Is that better, internet person? Hello?
I texted her.
Okay, well.
You know, like a direct line.
Yeah, I mean, like it has little bars here, so I think it can hear me. Unless, I don't know, if she's watching the other one. It seems like it's going. I don't know. What was that?
She said no, just bouts of static.
On YouTube or on the other one? There are two different recording technologies.
Oh.
All right, well, we do that. In terms of announcements, your next homework is due next Wednesday. Judging from the people in my office hours, this is one of the more challenging ones. So if you haven't gotten started, you should. That's my main message. And then, of course, we'll continue to have nano quizzes, I guess, basically go out. It's every other lecture. So for now, it'll be on Tuesday. What now? The other one's failing. Okay, but the YouTube seems to be going okay. That's good. That's the one that, you know, gets me the followers. All right, so today we're going to start the next big chunk of 6837, which is probably the part that you actually think of when you think of computer graphics, which is rendering. So if you recall, basically the way our course is organized is basically following the graphics pipeline, right? So we started with some abstract stuff, and that's because we started with the sort of bits and bytes version of how you store a scene digitally on a computer. Now that we've described the scene, we need to actually draw it on the screen. And of course, that, I think, is the core piece of computer graphics, and that is rendering. So, as a bit of a review of our story so far, basically we've talked about modeling problems, right? So modeling being coming up with a description of a scene and then how it moves around, like animation. We've talked about many different types of animation, right? From differential equations to skinning and so on. And you're going to implement that in your homework if you have not already. And now that we have all that, we're going to actually generate our scene. And so that's basically our task for today. We're going to talk about what does rendering mean? Like what is it, when we talk about specifying a scene and putting it onto the computer screen, what are the relevant vocabulary terms here? And then we're going to talk about the basics of an algorithm called ray casting. You've probably heard of ray tracing. Ray casting is basically the same thing, just even simpler. I confuse those terms a lot, so if you hear me say ray tracing for purposes of today's lecture, I mean ray casting, but it really doesn't matter. Okay, so the basic task of rendering, I think, is a pretty straightforward and intuitive one. It's one that we all know and love, and probably the reason you're all taking this course. Essentially, you know, you have your camera, which is either an actual physical camera, or in the case of like writing software like OpenGL, of course, it's a virtual camera, which is specified by a pose, a direction, you know, focal length, whatever. And then essentially your job is to create this like little two-dimensional square worth of pixel colors, given a description of all the objects in the scene. That sounds simple enough, but of course rendering is a really challenging problem for so many different reasons. So today and in the next couple lectures, we're going to set up the basics. Like what does it mean to light up a pixel here? What objects should we put into each pixel and what color should we give it? And then rendering gets more and more difficult from there, right? We can handle things like shadows and diffraction and refraction and rainbows and all of our favorite visual effects and how light interacts with different types of matter. But that's actually not the only challenge in rendering. So for example, one of the really neglected things that we don't think about until we look at our first rendered image and realize that it's garbage is that at the end of the day, you can think of your rendered image as kind of like holding up a little screen door in front of your face, right? And in every little square of that screen door, you have to decide on a color, right? That's really what rendering is. Here's the problem. In the real world, is there just one color in every little square of your screen door? No, there are many. You know, like if I hold it over here, I see an orange T-shirt, some black sweatshirts, a lot of black. You guys are it's kind of a, it's like a funeral in here. But in any event, the basic point is that in a single pixel, there might be many colors, and we have to come up with just one decision of what to light up, right? And that problem in itself leads to a phenomenon called aliasing, which is something that we'll also talk about quite a bit in this course. So for now, we're going to make a simple assumption, and then we're going to violate it later, which is that we're going to send a ray right down the middle of that square in our screen door. And then whatever color is right at that midpoint is the one that we're going to assign to the pixel. And of course, that creates for some weird phenomenon, right? Like if I have an object that's kind of panning across an image, then like, a pixel will be like the background color until it crosses right the middle of the pixel, and then suddenly it'll like change. So that's going to create some weird discontinuities that we're going to address later. Okay, so that's the basic challenges of rendering. For now, we're also going to make another assumption, which is that we're using a pinhole camera. Have you guys heard of this phrase, either in photography or in computer graphics? The basic idea is that our camera lens is a sort of infinitesimally small little aperture here, and that affects like depth of field and so on. Depth of field being like I focus here, and the gentleman behind me is blurry, Maxime. Those sorts of effects can't happen because I've got this idealized little lens in front of my camera. Later on, we'll talk about how to fix that, because it turns out that the ray tracing algorithm makes all of these things extremely easy at the cost of a lot of computation. That's going to be our trade-off in the next couple lectures. Like, we're going to be able to make really nice-looking images with like only a few lines of code, and that's super cool, and it's really exciting, and students get really carried away with this. And then they realize that like they ray trace the scene with like 3 spheres, and it takes like an hour and a half, and then it becomes a little less exciting. So we're going to address that as well. So of course, the very first thing that we have to do is we send out this ray through, for now, the center of our pixel. We figure out what object it runs into, and then we have to actually light this thing. And so we also need to talk about shading, material models, and so on. Right? So there's all kinds of different ingredients that we have to stir together to make a rendering algorithm. And the nice thing is that they tend to be quite modular, right? We can develop each of these pieces one at a time, put them together, and keep adding features to our rendering tool. Okay, so to kind of fill in some vocabulary terms we've already been using here, the term rendering refers to this entire process that goes from, a description of a scene to the actual color values on your grid. Each pixel in your image, for now, is going to correspond just to one ray. Eventually, we're going to see that taking a weighted average is probably a better idea. And we need to do a lot of different calculations. We need to figure out what's visible in a pixel and what color it has. And there are many different ways to do that. So in this course, we're mostly going to talk about 2 techniques for rendering. One is called ray tracing or ray casting, and the other is called rasterization. There's sort of a goofy way to describe the difference between them, which is just the order of 2 for loops. We'll see that in a few lectures. But then what's going to happen is that even though the basic algorithms really are just like there's 2 nested for loops, one over pixels and one over objects, in which one is on the outside, determines ray tracing versus rasterization, that the way that you accelerate those 2 algorithms is quite different. Okay, so ray tracing is going to kind of be our example of like a CPU-style parallel coding style algorithm. And then rasterization is going to be something that makes sense for your graphics card. Now, these days, the line between those 2 is getting blurred a lot. In fact, I just saw an advertisement a couple days ago for like, I think it was a Nokia phone apparently now has ray tracing built into its hardware. Samsung? You might ask why? That is a question that I too have. But I guess it's a nice way to show off the computing power of your phone and also burn a hole in your pocket. But anyway, metaphorically and physically, like it's a lot of computation. So in general, what we'll see is that it's really easy to get nice effects in ray tracing, which is why people talk a lot about like, can we do real-time ray tracing? Because like you could capture all kinds of cool visual things that would be hard to rasterize, but the computational trade-off is quite different. Okay, so here's our basic outline for today. We're going to talk about the ray casting algorithm, which is basically just sort of like a technique for rendering that deals with visibility, right? So if we draw a scene with multiple objects in it, today our objects are going to be spheres and planes. They're going to be very exciting 3D scenes. Then we need to figure out which one's on top and then how to light it, right? And that's what we're going to do here. We're not going to deal with reflection or soft shadows, any of that stuff. That'll come later. Okay? So we'll tell you a little bit about just the basics of the ray casting algorithm. In particular, we need to figure out what rays to cast, right? So we need to figure out the direction of the rays that we're going to kind of launch out of our camera into the world. That's part one. And then part two is like, okay, we send the ray out of our eye. We got to figure out what it runs into. And we're going to work out the case for a plane and a sphere. That sounds goofy, but those two things together are going to get us pretty close to essentially what we need for ray tracing. Because next lecture, we'll talk about rays into triangles. And as we all know, basically all of our 3D models are built out of triangles in computer graphics. So if we can render one triangle, then we're pretty much good. So that's going to be our task, and that's going to be built largely on the math that we'll start with today. Today's math is going to be a lot of review from pre-calculus class. I think this is not going to be like super complicated, no integrals or differential equations or anything. But it's important to kind of call it out and remember all this stuff for what it is. All right, so in case you were wondering how to render an image, you got it. It's on the screen right here. Here is the ray casting algorithm in its full glory here. So it's quite straightforward. Essentially, if I want to draw a scene using ray casting, oh, I'm sorry, I got this thing here. What do I do? Well, I'm going to loop over every pixel in my image, which again, I can think of like a little virtual screen door sitting in front of my eye, right? That's really what it is. And now I'm going to loop over each pixel. And for each pixel, I'm going to construct a ray from my eye through that screen into the world, right? That's this pinhole camera model. And so the ray here in this diagram is that red line. Yeah? And my task is to figure out what object that ray hits into first, because that's the thing that I should draw on the screen. Does that make sense? So how do I do that? Well, I have a for loop over every object in my scene. Like in this case, what, 4 spheres and a cube? And for each one, I figure out the location of the intersection. I choose the one that's closest to my eye, and that's the one that I draw. Right? And so that's the one that I shade. Of course, I have to be a little bit careful when I say closest. So for example, what if there's a sphere like right behind my eyeball? That might be quite close to me, but of course I don't see it, right? So there's a signed effect here that we have to be a little bit careful about with our code. Does that make sense? Yes? That's a good question. So this picture is a little abstract. The eye, I think we typically think of it as sort of this model of like the eye is really just a point, and then there's like a little rectangle sitting somewhere in front of you, and then the ray generation model goes from that point through a grid that's sitting on that rectangle. That's right. Yeah, so the grid is kind of like your 2D screen. But there are many different, basically equivalent versions of that story, right? A different one that I think you see a lot, especially in perception, is to talk about field of view. So that would be like your eye plus a direction out plus an angle, which is how wide this kind of cone is. And these are all just equivalent, right? You can convert from one to the other pretty easily. Yes?
If you had the sensor for a camera, it means that actually it's not the sensor, it's not the black thing. You would have another grid.
Ah, yeah. So there are no sensors. This is a virtual environment. There's no actual camera. If you wanted to simulate a camera, the sensor would actually be behind the eye, right? So in a pinhole camera, what really happens, you have your world. So here's a tree. It's a happy tree, and actually it looks kind of like that screen painting. And here's the eye. You know, so here's my rays, and then in a pinhole camera, the sensor actually sits behind the eye. And what you get is like your rays go through the lens onto the back screen, and you get an upside down version of the image you're trying to make. That's very difficult to do in real life. Pinhole cameras are tough because an infinitesimally small hole does not let in very much light. Yeah. Okay, great question. Any others? So one thing that we're going to defer on for today's lecture, but we're going to come back to in excruciating detail later, not to worry, is shading. So we already have one shading model under our hands here, which is the Lambertian shading model. Remember, that looks like dot products, right? So the Lambertian shading, I compute a vector toward the light, I compute the normal vector, I take the dot product, and that's how much I kind of attenuate the light once it hits the surface, right? I think you all implemented this on homework 0. And so Lambertian shading makes ridiculously boring things like this diffuse sphere that we see on the screen here. It's basically the terracotta shading model. Later on, we're going to talk about many other models. We're going to talk about specular shading, so that's stuff that's a little bit shiny. Maybe we include environment maps so that we actually kind of have a reflected universe off of the side of our shiny object. And more generally, we're going to define objects called BRDFs, which are essentially this function which says, like, for every in and out angle, how much light comes in this way and bounces out that way. But we're going to talk about that more in detail in another week or two. So for now, by the end of today's lecture, our goal is to design scenes that are comprised completely of diffuse spheres. In fact, they're all going to be centered at the origin, too. Just so basically, you can draw one scene. But that's enough to get started. OK. So I mentioned a few times that ray casting and ray tracing are not the same. I think a lot of people in the graphics community basically use these terms interchangeably, so I'm not going to like give you a quiz question and ask you to explain the difference between the two. But in case you're wondering, roughly, the difference has to do with whether you have something called a secondary ray. So let's say that I want to draw this scene here. So I've got the camera on the right here, and I've got a sphere and a cube. And it's being lit, and the light is sitting kind of above the cube. So is the sphere lit? No, there's a cube in the way, right? And so the reality is when I render the sphere here, you know, it should make it some dark color, or maybe not draw it at all, because it's not actually receiving rays of light from that light bulb. But when I actually draw the scene, and using the ray tracing algorithm I've described for you so far, what would I do? Well, I'd send out a ray from my camera, it runs into the sphere, and indeed, that's the object I should draw at that location. And the question is, what color? Well, if you use the Lambertian shading model I've given you so far, what would you do? Well, you know where the light is, you know the normal of the surface, you take the dot product, and you've got the color. Of course, that's wrong, because you really shouldn't light the sphere at all here. So in the ray tracing algorithm, what could I do? Well, I could notice the following, which is if I draw a line from the sphere to the light bulb, if there's an object in between, then the sphere doesn't get lit, right? And conversely, if there is no object in between, then I should light it, right? Do you see how that's exactly the same piece of code that I'm using to figure out what object to render? So in other words, I send one ray from my eye into the world to figure out like which thing is closest to my eye in terms of just what object to render at a pixel. Now I can draw a ray from that intersection point toward the light bulb and just call my same piece of code saying, does something hit that ray? And that's going to be what I use to determine whether to shadow or not. So essentially, this one little piece of code that we're going to write, like given a ray, what's the first thing it runs into, is going to get reused over and over and over again in the ray tracing algorithm. So in ray tracing, basically, we just make that extra little observation that this little abstract piece of code that inputs a ray and outputs the first thing it runs into is just really handy in rendering, and you can use it recursively, right? So like, I first run into the sphere, and then I recursively make a ray off toward the light bulb and see if that runs into something to figure out how to light it. Does that make sense? Yeah, so I think this stuff is pretty straightforward to start. Obviously, we're going to keep adding layers and layers of complexity. The good news is that writing a ray tracer is a really elegant exercise in coding. I would argue that your homework 2 is not so much the case. There's a lot of complexity there, and there's a lot of moving parts, and they hook together in really complicated and annoying ways. A ray tracer is sort of the opposite of that, right? Like there's this abstract thing which is an object, and does it matter whether that object is a sphere or a plane or a bunny or what? Not really. It's just a thing that takes an array and tells you when it hits it, right? And so there's a really nice abstraction that's going to happen here, and it's going to make it pretty easy to render. Okay, so anyway, that's our main distinction between ray casting and ray tracing, is whether or not you use these secondary rays. This is just an academic thing. I don't think it really matters a whole lot. As long as you implement something that makes a nice visual image, I don't care what you call it. And of course, ray tracing allows you to draw all kinds of scenes that involve checkerboards and shiny spheres, which tend to be what undergrads have to implement a lot in their ray tracing classes. We have shiny teapots. This teapot has an environment map. That means that like there's some like sphere around the teapot with like a photograph of the world kind of nearby that's like kind of reflecting off of it. On the left-hand side is the very typical test image that we have for ray tracers. The reason this is kind of a useful test image is, of course, when you run into that reflective sphere, you have to generate a secondary ray that bounces off of it to figure out the color. So this is a good kind of test bed for this sort of thing. So this recursive ray tracing algorithm that I've described for you so far, right? So I run into something, and then I generate secondary rays. So for example, for lighting, I generate a ray toward the light bulb and check occlusion. Or maybe for this mirrored object, the secondary ray just bounces the ray off to do shading. Is that it? Like, is that physics? We're done? Like, that's going to make all the beautiful scenes I could possibly want? Yeah, what am I missing?
Kind of like diffuse lighting, maybe, like something that's just generally there. Like, I mean, I would imagine that we can get very dark kind of regions if we just have like if we just have the sun somewhere and then just have one plane kind of occluding a sphere, it would just be completely dark. But I mean, that doesn't seem realistic. Kind of.
Yeah, I think you have the right intuition. Let's see if we can think of like a very specific effect that might be hard to capture. Ari, yeah?
I was just gonna say the way that light objects are lighted and then how objects interact with each other
Mm-hmm.
that way, and how like I was just thinking about when you have the cube over the sphere, how the cube casts a shadow. You need to calculate like the exact way that that cube is gonna cast a shadow because it's gonna cast a shadow differently than it would.
So I think our secondary ray method will deal with the shadows okay, but there's some effects that are going to be a little bit trickier. So soft lighting actually might be okay in ray tracing. So for example, if your light has a big kind of area, maybe I randomly draw the location in my shadow calculation. That would probably take care of that particular issue. How about some other effects? What can we think of that might be hard to account for with secondary rays? Yes? So light reflecting off of other surfaces can, well, give me an example actually, it depending. Like the spheres on the left-hand side, these are made with ray tracing.
If you're like in a room, like you roll the light and you have like a point light,
Mm-hmm.
blocking it, so like the light can still reflect off the sides of the walls and like go to the back.
That's a great example. So here's an image. Does anybody know the name of this image? I'm sure Zoe does. This is called the Cornell box. This is a famous kind of test image for rendering. So you've got two spheres, one of which is reflective, one of which is refractive. So like one's glass and one's a mirror. You have a red wall, a blue wall, 3 white walls. And as our colleague has pointed out here, there are many effects in this room that are hard to capture using that ray tracing algorithm. So one of them is the fact that the floor is ever so slightly blue close to the blue wall, and ever so slightly red close to the red wall. Right? But that ray tracing algorithm isn't going to see that, right? Like I send a ray from my eye to the floor, and it just sees a white floor. Like how does it know which of the many locations in the scene is casting just a little bit of red onto the floor, a little bit of blue? Right? That's a tricky thing. I see, I'm going to catch you in just a moment. A different effect, which is hard to capture using this technique, we'll talk about all these later, is something called caustics. Right? So like think about having a magnifying glass that takes the light and then focuses it on a point on the ground, like what you see on the right here. If you think about the path of the light that takes to go to this point here, it goes through the object, bounces, and then hits the ground. So in order to figure out that I'm inside of this like bright region here, I have to solve a pretty weird problem, right? Because I have to figure out like what sequence of bounces got me all the way back to the light bulb. And so these are the sorts of effects that are really hard to capture with this algorithm. These are called global illumination, and we're going to come back to these later in the course. I just want you to start kind of thinking about the limits. Yes, your question.
I just always kind of ask is, couldn't we do a thing where like, at least with like the red walls and stuff, you could like color the rays bouncing off, like it would be like a color reflection?
It's a good question. Yeah, so the question is, can you color the rays? The answer is absolutely yes. Like, in fact, that's roughly how we're going to implement a ray tracer. The question is, which ray? So like if I have a point on the floor, which is just like ever so slightly reddish, is that red color coming from the middle of the wall? Is it coming from the bottom? In the ray tracing algorithm, I kind of have to know because I have to trace backward to the light source. And that's where things get a little tricky. Great idea. Any other questions? I want you guys to think critically about this algorithm because it's kind of nice to put your feet in the history of these rendering techniques. Like this is a really simple method. Although amazingly, I mean, the original ray tracing paper was like, late 70s, early 80s? Like it's not as old as you might think. Really, that's not old. And, you know, in the history of computer science, it comes remarkably late relative to a lot of the developments that you study in undergrad here. Yes?
Given that we have to solve these like hard problems about tracing back to the light, why not just like cast the rays from the light and then have it bounce around and whatever?
Oh, you guys are asking all the right questions. So the question was, okay, so the algorithm I've described for you traces rays from my eye back to the light. Why not trace rays from the light to your eye? I think that's right, but let's say that I see it. Let's say that I have my light source, and I randomly draw a ray from my light source, and I follow, and indeed, I can bounce it all around the scene. What's the probability it's going to hit into this infinitesimally small eyeball that I have? 0. Right? So the vast majority of rays that come out of the light bulb don't reach your eye. Right? What was that? Yeah, that's right. So one thing I could do is try to actually solve that inverse problem. And indeed, some global illumination methods really do try to do that. Or they'll meet halfway. So maybe they'll cast some random rays from the light bulb, attach them to points in the scene, and then do forward ray tracing from your eye and figure out if there's anything nearby. And that's some approximation to the kind of problem you're talking about. Yes? Okay. Excellent. So hopefully I'll convince you all that like this is the tip of a ginormous iceberg. This is like one of these really fun areas where you can just keep adding cool effects to your ray tracer and capture all kinds of things. And in fact, as you walk around the MIT, MIT is kind of ugly, but if you walk around outside in Boston, take a look around you and just like look at all the interesting materials and visual effects that you could capture just in a simple scene. I mean, one of the joys of teaching in this, one of the few joys of teaching in this classroom is this tiny little corner of the Charles that we can see right out the window here. And, you know, just walking along there, I mean, there's so many neat visual things that are going on as the light bounces around the world. And each one of those can be some interesting little piece of your ray tracer code should you model it in just the right way. Some of them are easier than others. For example, like transparent objects are another tricky matter, right? Like where does the ray bounce? Does it go through? Does it scatter? What? All kinds of good things. In fact, a good one is marble, right? If I hold up a light bulb onto a piece of marble material, the light scatters in the interior and kind of glows outward. And so in that case, the light doesn't really take a linear path the way that we've drawn here. So hopefully I'll convince you that basically the algorithm we're going to derive today is garbage. You know, like we're going to show the simplest version of rendering, and that really rendering is much more complicated, but this is like the baby steps in the right direction. That's my point. I'm enthusiastic because I love this stuff. This is fun. Like this is how I got into computer science. I found a textbook on ray tracing by Pete Shirley in a bin in a crappy bookstore in Ocean City, Maryland when I was a kid, and somehow now I'm going to have a terrible midlife crisis when I realize that my whole career followed that path. Right, so let's talk about ray tracing in a little more detail and actually do a little bit of math. Okay, so the first thing that we have to do is talk about how we might store array on a computer. Like, what does it mean? Like, I've drawn you this cute arrow with this little like eyeball thing. Like, how would I store that computationally? Anybody have suggestions? I mean, we've talked about coordinate systems and everything else. Like, what would be a reasonable way to represent array? Yes?
A point of origin and a vector away from it.
Yeah, a point of origin and a vector away from it. Fabulous idea. So here's a very simple way to represent array. Is as a parametric curve. We've already talked about those in this course. Sorry, you can't escape. Good news is that rays tend to be straight lines. Not always, but they tend to, in this course at least. And so a reasonable way to store array computationally would be to store basically 2 vectors worth of information, right? Like where the ray starts and what direction it's moving in. And of course, this representation is not unique in the sense that like, I don't have to make that direction vector a unit vector, right? So there are different ways to specify basically the same object. Any questions about that representation? If you don't get this, it's going to be a really boring lecture from here on. Okay, so now we can kind of phrase our ray casting problem in a little more concrete language, right? Specifically, so we have this function p of t, and then we have a list of objects in our scene. So can anybody articulate the computational problem that we need to solve, like in order to figure out what we're trying to render? Yeah.
I'm going to try something, but I guess we want to first see like collision or intersection with objects,
Mm-hmm.
and then find the closest one.
Sure. So in the language that we've established on the slide here, the way I would put it is that you're trying to find the smallest t, which so that p of t hits the surface of some object in your scene. And there's one detail, which is the most common bug when you start to implement this kind of thing. I guarantee at least one person in my office hours will have this bug, which is that it's a smallest positive t, right? Because if there's an object behind your head, you shouldn't intersect that with the ray. Okay, so that's really our task for today, and this is our basic ray object intersection problem. And what we're going to see is that when we have a piece of code for doing this, that's like 83% of what we need to do all kinds of cool rendering effects. Yes? That's a good question. So no is my short answer. So T is how far along that ray you've gone, right? We haven't introduced that grid yet. Yeah. Now the ray tracing algorithm goes back a lot farther than the 1980s. In the sense that actually in the 16th century, people were already doing some kind of analog version of ray tracing. So here is one of these famous, what do you call these things? Etchings of ray tracing as some of the early technology for getting perspective correct in art. So here you can see that they're actually, Dürer is simulating the pinhole camera by having a piece of string which he's attached to the wall. So the wall is kind of like the location of the pinhole camera. They've got this little square here, which is like the thing that they're going to draw eventually. And then he's just holding the string to the different points on, is that a lute? I think it's a lute, to get the perspective right. And you can see he's really showing off here, right? That lute is like at a really funky angle. That would probably be hard to draw if you're a, 15th century artist. And there are many different variations of this technology, as it were. So here's another one. This time, the relative positions of these different pieces of this device have changed, but the basic technology, being a piece of string, is roughly the same. At one point, I actually tried this in my office, and I totally failed. It's actually much harder than it looks. Yeah, like I'm a horrible artist, but like this only made it worse. Like it was really quite frustrating. But I digress. So anyway, essentially what we're implementing here is just the computational version of the same thing, right? Like we're drawing that ray from our eye, and then we're kind of pointing at an object and figuring out which one it hits first. Okay, so now we got to do a little bit of math. I'm sorry. In particular, we got to do two things. One is we have to actually produce the ray for each pixel, and the next thing we have to do is run that ray into each object in our scene. Right? And that's going to be how we basically spend the rest of today's lecture, is producing the rays for this simple pinhole camera model, and then intersecting those rays with spheres and planes. And then, of course, a triangle is a piece of a plane, so we're about halfway there toward the real rendering thing that we need. Okay, so essentially we're dealing with this highlighted red part of our scene here, right, which is to construct a ray from your eye. I love these lecture slides. They continue. I don't know if, I think maybe Fredo probably strikes me as the kind of guy that like actually dug up these old historical images of the perspecteur, who I guess we're doing this in person, and of course smoking at the same time. Right. So we're going to simulate a pinhole camera, as we've already described, which is essentially just a giant dark cube where everything goes through a point and then casts an image on the back. Notice that like as I increase the aperture, like I move away from that pinhole setting, then things start to get blurry because not all the rays go through a single point, right? So when I look at like a pixel on the screen in the back, there are kind of multiple paths through that aperture that they could have come from. And that's what's creating that depth of field effect that everybody wants on their iPhone, right? Like when you go into that like object mode, and like the background becomes blurry, that effect cannot happen with the pinhole camera. Okay, as with just about everything in this lecture, pinhole camera has a very long history. So here's the slides claim that it's the oldest illustration. I will admit that I have not verified this personally. I also was not around in the 16th century, so it's hard to do. But the pinhole camera technology really does go back a long time. Essentially, if you wanted to like image the planets, you could create this, of course, very sophisticated Greek columned room with a tiny, tiny hole in the side, wait for just the right time of the evening, and see a very faint image of the outside world cast on the back wall. This was before Instagram, and so this was a pretty interesting technology for the day, but a bit more, you couldn't really scroll. You only got one image. And there are actually examples in architecture of this sort of camera obscura effect. It's really hard to pull off, and it requires a very bright light on the outside to do in real life. There's actually a really cool website. I encourage you to take a look. This guy, Abelardo Morel, is an artist who, I guess, seeks out interesting apartments that are like across the street from interesting places around the world, and then like sets up a pinhole camera so like you can see what is that, an upside down capital on the left-hand side, which is being cast into this person's bedroom by like some aperture in their window across the way. I'm sure that taking this photo required a very long exposure and a lot of control and no earthquake. Yes?
Why is it upside down? Does that happen in like graphics?
Yeah, why is it upside down? So this ugly diagram actually communicates it, or there's a better one in the slides. Right, so here's the outside world. Here's our pinhole. And then here on the back end is our imaging device. So what happens is the rays pass through the pinhole and onto the screen in the back, and when they do that, it inverts. So, no, yeah, that's a great question. So when we actually implement a ray tracer, we kind of put a virtual screen in front of the eye, because I think it's just easier to think about. Yeah, there's really no reason to do the extra math of flipping your image over. Yeah. Excellent question. Any others? Okay, quiet bunch. Right, so here's a better illustration of exactly that, right? So of course for us, like we don't have to worry about being in a dark room or anything else, so we can just put our virtual screen in front. And notice that basically there's like some kind of a pyramid sitting in front of your eyeball, which is like, let's say I put my square image like 1 foot away from my face, then the amount of stuff that's visible as I get closer to my eye gets smaller, and as I move farther out, it gets bigger, right? So this whole thing cuts out a pyramid shape. Anybody know the name of this pyramid? I'll give you a hint, it's on the slide. Yes, this is called the frustum. And if you've ever played with graphics tools, the term frustum comes up a lot. Because that's essentially sort of a volume in space of things that would potentially be visible on your screen. Very often we talk about frustum clipping, which in addition to this also clips depth that's too close or too far from the eye. That's less relevant to ray tracing, but when we talk about video games, that's going to be one way to like make your game faster, right? Is to detect that like objects outside of the frustum I don't need to render, right? So we can just throw them away. Yeah. So there are many different ways to describe cameras. To go back to a question we had before, here's a pretty typical one. This is a lot of letters for something that I think if you all sat down and tried to engineer, you'd probably come up with roughly the same thing. So I think a pretty typical camera description tells you where the camera is, right? That would be like your eye position E. And then it typically comes with an orthonormal basis, right? So one direction is like the direction out of your eye, and the other two directions are like the image plane, right? So like here, you can see the W direction is like the direction straight out of my eye into the center of the image, and then U and V are like to the right and up on the image plane. That make sense? I think so. There are other ways to describe cameras. A pretty typical one is to use a field of view, which would be kind of like the angle of the frustum toward the eye. And then, of course, one important detail that we have to account for is the aspect ratio. Typically, your computer screen, well, these slides are weirdly not a great example. Your screen tends to be like wider than it is tall. So it's not really a virtual square in front of your eye, it's something else. Right? So like 16:9 is a pretty typical one. That's what happens in cinema. So the aspect ratio would be like the ratio of the width to the depth, or height, or the other way around, I always forget. One term that shows up in graphics sometimes, so it's worth knowing, is normalized coordinates. When we talk about normalizing a vector, we mean dividing it by its length. When we talk about normalizing image coordinates, it's not quite that. Usually what that means is that we just map the lower left corner of the image to like -1, -1, and the upper right to 1, 1. This is just a convenience, because then when you produce your rays, you do them on a square. It doesn't really matter, but it's just a term that comes up a lot, so it's worth being aware. And really, it's just a question of rescaling those U and V. Many pieces of code don't even bother to do that. In the slides, I've given you guys the math for how to produce a ray if you are given the field of view and a depth from the camera. I'll let you review that on your own. I think actually even on your assignments, we don't do that. I think that's sort of an old school way to specify your scene. I think it's very typical to just give that out direction, the U, the V, and produce rays that way. Anything is perfectly fine. So there's some simple trigonometry you can do to kind of produce rays given the viewing angle, but I don't think it's too exciting. So we're going to skip it. Okay. This is the pinhole camera model. There are many other camera models out there. And in fact, they don't even have to be that physical, right? I mean, one of the really liberating parts of doing computer graphics relative to being like a physicist or an artist is that like our medium is extremely flexible, you know? Like if I want to produce rays that are launched from all kinds of weird angles and are mapped to pixels, I can do that. And some of them turn out to be quite important, both historically and for engineers as well as for artistic purposes. So the simplest example is something called an orthographic camera model. Many of you have probably encountered orthographic cameras before. So in an orthographic camera, essentially what you do is you generate all of your rays in parallel, right? So it's not like they go from your eye through the image plane. You just like put a rectangle somewhere and then just launch a ray out of that rectangle in some evenly spaced thing. The orthographic camera is actually pretty similar to the perspective camera, so long as there's nothing too close to your eye, right? Because then, like as you move farther away, the rays start to look kind of parallel. So does anybody know where orthographic things get used? Yeah. Yeah, like architecture and engineering. Essentially, one of the reasons that we either like or don't like the pinhole camera model is it has foreshortening, right? You know, like if I look at parallel train tracks, they don't look parallel in the computer screen, right? They look like they're converging as they move from the camera. That doesn't happen in the orthographic camera model. And so a lot of times, like when you're doing product design or something, and what really matters are like the angles that things meet up at or something like that, and depth is less important, the orthographic camera model can be useful. So oftentimes if you're using engineering software, like what's offered by Autodesk, there's just some little checkbox. You can turn it on and off and play with different cameras. I had a high school engineering drawing teacher that had us draw orthographic pictures of our toilets, and he thought it was the funniest thing in the world that all these high school students were sitting on the toilet drawing the mechanism. So don't do that to your students. But there are many other camera models out there, and they have all kinds of interesting effects. So for example, you might have a fisheye lens where like the rays are coming out of the eyeball in more of a circular pattern, right? Like what you see on the left-hand side. And like I mentioned before, I mean, a fisheye lens is an actual thing, right? You see it in like security cameras a lot because they tend to have a very wide field of view. But in graphics, we're not constrained by actual physical world. So here's a really fun example. This is something called multi-perspective imaging. I don't think this is terribly popular anymore, but sometime in the 90s, this was proposed, and for a little while, we were all playing with it. So here's a 3D model of an elephant. Multi-perspective imaging is really difficult to understand. So essentially what you do is like think of, I put a camera on kind of like a gantry or something, like it's on like a little circular track around my elephant here. And I take a bunch of pictures. So in other words, my elephant's standing still, I put the camera on a track and I move it in a circular path around the elephant. And now what I'm gonna do is take the first column of pixels to be the first column of pixels from the first image, the second column of pixels to be the second column of pixels from the second image, and so on. So in other words, every column of pixels is drawn from a different image. They're all composited together. But that's how I might do that physically. Here, of course, I can do it by just creating rays in a carefully chosen way. And what you end up with is kind of interesting. It's like an unrolled version of the 3D world, which I think was originally proposed because this is some way to get like many different perspectives on a scene in a single image. So is this like an effect that you all need to memorize and implement at home? No, but like it's a cool example where like by just remembering that like we don't have to create rays that imitate an actual camera, we can do some pretty cool stuff, and sometimes it's quite valuable. I think you can go on YouTube and find some interesting animations that are drawn in this camera style, and they're very hard to process mentally, at least for me. Is there a question, or you're just, okay, cool. Are there any questions about like this ray generation model? Yes?
This is fairly tangential.
That's okay, I like those.
Like create camera created to like model an animal view, like predatory, like where eyes are based. Like, is there any biological based cameras?
Are there any biologically based cameras?
Like this feels like it's trying to recreate some other perspective.
It's an interesting question. Like if you want to, you want to see the world like as if you were looking through your pet cat's eyes. Yeah, okay, short answer is I have no idea. But there are some technologies that are close. So for example, when people are modeling lenses, it's very typical to use exactly the ray tracing algorithm that we'll talk about to actually engineer the shape of a physical camera lens. So I would imagine that people like optometrists actually are using very similar math, and I don't see why you couldn't invert it and use it for image generation. I can't give you a specific pointer. It's a creative idea. I don't know. Yeah, if you guys find anything, let me know. I'd be curious. Okay, so far we've talked about our array generation model, right? We know where the camera is. We know where our virtual screen is. We stick an arrow from one into the other, and now it's launched off into the world, and our task is to figure out what thing it runs into first, because that's the thing that we're going to render. And so our next piece of math that we have to do is to actually kind of do that calculation. Remember, it's find the smallest t that's greater than or equal to 0. The equal part is debatable. That runs into a particular object. By the way, what we're going to find in our next couple lectures, we're going to have to build lots of like epsilons and tolerances into our ray tracing code. And that like find the smallest t greater than 0 is a good example. Like how much greater than 0 is greater than 0 is a good question. And it's a tricky matter. Okay, so essentially now we're dealing with this new, this line of code that's highlighted in red, which is to find the intersection between our array and the objects in our scene. Okay? Cool. So here's our array representation. Remember, it's got an origin and a direction. We would call this an explicit representation of the curve or a parametric one. Remember, parametric curves are things that like take in a t and output a point on our curve. And essentially, our curve is valid for any t bigger than 0. All right, so the first thing that we might do is try to put a ground plane in our scene, because again, the only scene we're going to be able to render by the end of today is a sphere sitting on the plane. And so the first thing we need to do is intersect rays and planes. So of course, the first question we have to answer is how to represent a plane on a computer. Any ideas? How could I store a plane on a computer? There are many options here. Yes? Two vectors. So what would the two vectors represent?
It just represents the aim. Take the origin, you take two vectors, and then the plane is like everything as a linear combination of those 2 points.
Sure. But that plane,
Vectors aren't like the same scale.
that plane would have to go through the origin then.
Yeah, that's why you have a point for the origin.
Okay, so I think we could probably come up with a more compact version. Let's keep thinking. Yes?
Sort of one normal vector and then like a point that passes through.
Yeah. That sounds like a good suggestion. So the suggestion was to store a plane with a normal vector and a point on the plane. Yes?
And we could make that even more compact if we just stored it implicitly.
If we store it implicitly. And in fact, those two things are the same.
Well, two less numbers to store it.
Let's see if that's really the case. So let's think about it for a second. So, cool. So let's do some math here. Right, so here's a plane. You can tell it's a plane because it has 4 corners, which is a lie because planes keep going, but for some reason that's the only way we know how to draw it. Okay, so the suggestion, which was a good one, is that we store a plane by storing 2 pieces of information, right? Like a point P on the plane, and then a normal vector, which is 90 degrees to our plane like that. That's an N, in case you're wondering. Right? And so then the plane is the locus of all points that are in this rectangle here. How could I express that mathematically? Let's say I have a point, I don't know, what's our favorite letter here? Q. Yes? Yep.
Q minus P is orthogonal to N.
Yeah, so if I draw a vector from P to Q, notice that vector is in the plane, right? So it should be 90 degrees to the normal. So in other words, our plane is kind of defined by this relationship, right? Which is the normal dot product, maybe Q minus P, like that. Does that make sense? And now, of course, I could take this product and I could expand it, right? I could write this as the set of all points Q that satisfy this relationship, where I take the dot product of N and Q minus N dot P, and I get 0. And this number here is really just a scalar, so I believe what our colleague was suggesting was to just store this as some magic number C, right? And essentially, your plane is basically the locus of all points Q, where the dot product of your normal and Q is some constant C. Right? So this is just a reasonable representation for a curve. I doubt that off the top of my head I've managed to choose the same letters as the slide. Yeah, not quite, but this is the same idea. The main takeaway here is that when you look at the equation of a plane, I think one thing that we kind of know, but maybe we haven't thought about carefully, I think we all know that like a plane is really like ax plus by plus cz plus d equals 0, right? I think we'd all agree that's a plane. the key thing to kind of observe here is that the a comma b comma c vector, right? If we look at this formula here, you can see it's just the normal to our plane. Right? So really it's a meaningful formula. And then d here is kind of like controlling the displacement of the plane, right? Because it's kind of like the location of this point P. Any questions about that? I think we've all seen this before in some version or another. Okay. One kind of nice observation that I'll let you check at home, good linear algebra exercise. If n is a unit vector, then essentially if you define this function h of p, like ax plus by plus cz plus d, then that's really giving you the signed distance to the plane. Signed meaning that if a point is above the normal, then you get a positive value, and if it's below, you get something negative. Right? And this just has to do with like dot products giving you projections. Okay, so right, we're gonna switch notation ever so slightly so that I agree with the slides here. My apologies. So in particular, we're gonna say that our plane is given by the locus of points where the normal dot the point P plus some constant d is equal to 0. Sorry, I should have peeked before I started writing on the board. Okay, so this is our plane. And then we have array, right, which is given by r naught plus t times rd. And notice that, like, sort of spiritually, we're doing something a little funky, right? Like, our plane is defined implicitly, right? Like, it's the set of all points where this thing is 0. And our array is defined explicitly, right? Like, I'm tracing out a curve as a function of t. And I have to run one into the other. Does that make sense? So again, our array is p of t equals r naught plus t rd. And my apologies for switching notation ever so slightly. So what should I do? If I want to intersect my array and my plane, how could I go about that? I know you all know the answer. You're just quiet. I can set them equal to each other. That's sort of the right idea. But what do I set it equal exactly? This is an implicit relationship, and this is like a curve. Yes. Yeah. So remember that this is the point along our array that we want to be on the plane, right? So I can take this function p of t, which is like tracing some straight line, right? And then the place where it actually runs into our plane is exactly the one where when I plug p of t into this relationship, I get 0. That make sense? So let's actually write that out, right? So what do I get? I get n dot p of t, which is r naught plus t times rd plus d is equal to 0. And what should I do? Well, now I can just solve for t, because remember, that's our task at the end of the day, is find the smallest positive t that runs into an object. Yeah? Well, luckily for us, this is a linear relationship, right? This isn't too hard to work out, so let's just do it. So what do we get? So we can expand the parentheses here. So this is n dot r naught plus t n dot r d plus d is equal to 0, or t is equal to n dot r naught minus minus n dot r naught minus d, all that divided by n dot r d. Right? I think I managed to get that right. Notice, so this gives me a value of t. What could I do if I wanted the location of the intersection? I have t. I have p of t. Right? So I could just compute this t and then drop it here, and that would give me the actual location. That make sense? All right, let's see if I managed to do arithmetic correct. It's a kind of a, got about 50% odds in this course. Oh, I did. See, I can do math. I have a PhD in it. Okay, so, right, so there's our array plane intersection, and now you have all of the ingredients you need to make super cool renderings of planes. Whenever we write a piece of mathematical code, of course, we should check a few boundary cases and make sure that, like, our code is doing something sensible. And in particular, one thing to always be sensitive to when we're writing numerical code is division, right? And what could go wrong when we divide? Division by 0, yeah? And indeed, there's some possibility that that could happen here, right? I could have division by 0. And the question is, what does that mean in this picture? Do you guys, like, let's reason this through geometrically. Yes?
Well, if they meet infinitely far away, then it means that the vector from the eye is parallel to the plane.
That's exactly right. So the vector from the eye is parallel to the plane. And you can see that here, right? Because n dot rd equals 0. Remember, rd is the direction of the ray. N is the normal to the plane. Right? So it's saying, like, the normal to the plane is perpendicular to the eye direction, right? So in other words, like, that ray is just moving parallel to the plane. So that division by 0 makes sense, is basically my point. Of course, in your code, you got to check for that case, right, and handle it carefully. Or you kind of don't. It's probably okay here. Chances of that happening are pretty slim. Unfortunately, ray tracing, because we generate so many rays, these little boundary cases do come up, which is annoying. Okay. So of course, in our ray tracer, doing this calculation isn't quite enough. There's some additional bookkeeping we have to do. We're iterating all over all the objects in our scene, so we also have to make sure that that t is smaller than, like, any other objects we've already seen. And we need to make sure that it's not an object behind your eyeball before we keep that intersection. Yep, just some things I'm going to keep reminding you of today. That makes sense? And of course, we need that normal direction for shading as well. But conveniently, the normal is in our formula for the plane, so that's not terribly difficult. And now we have everything we need for rendering. Okay, so now we've leveled up our ray tracer. We can now draw flat stuff, but only flat stuff that goes on infinitely long. And our next lecture, we'll talk about how to deal with triangles. So in other words, like, when I render a triangle, I have to do two things, right? One is figure out when I hit the plane of the triangle. The next is when I hit that plane, am I actually inside of that triangle? It's that second piece of the calculation we're going to do next time using a piece of machinery called barycentric coordinates, which are a large part of my everyday life because I study triangle meshes. Okay, so in the last part of our lecture, we're going to make our 3D scenes even more exciting by adding spheres. And the reason we talk about spheres is that they're going to show us some of the things that can come up in ray tracing that we have to deal with a little bit carefully. It's also a nice example of something that's a little bit tricky to do in rasterization. It's actually not obvious how to rasterize a sphere. I think typically we don't even cover that in undergrad level rendering course. Whereas in ray tracing, it's very easy to kind of extend your ray tracing code to handle this other kind of surface, even though it's not comprised of triangles. In fact, almost any algebraic surface is pretty easy to render, at least if the degree is kind of low. So if you want to, like, render a hyperbolic sheet or something like that, it's just a question of working out the ray sphere or the ray object intersection formula. In fact, it's also a great way to generate, like, exam problems, like render this weird algebraic thing I just made up. Okay. Incidentally, that's also important. Like, we talked about B-spline surfaces, that kind of stuff earlier in this course. These are pretty easy to ray trace by kind of just solving algebraic style problems. In rasterization, it's not so obvious. We have to take those surfaces and, like, cover them in triangles before we can render them, because basically rasterization only knows how to cope with triangles usually. Okay, so hopefully we've noticed the pattern here. The first thing we do is talk about the object we're trying to represent. The next thing we do is run a sphere into it, or a ray into it, rather. I think I can spare you guys the trivia game here and just give you a spoiler, which is that if I want to make an implicit version of a sphere, it's relatively easy to do, right? So where did I put my chalk? Here's my sphere. You can tell it's a sphere because I'm going to give it a seatbelt, like that. And my sphere, I'm going to assume, is centered at the origin, and that it has radius little r here. And I've got a point P on my sphere, right? And of course, we know that the sphere is defined by all of the points that are a fixed distance away from the origin here. So one way to write that in our sort of implicit form is to write a function h of p, which looks at the norm of p squared minus r squared. And of course, this should equal 0, which is the same as the norm of p equals r. Now, there's a reasonable question, which is why did I put that square there? And the answer is just for convenience. Like, it's not strictly necessary. It's just going to make our math easier later. So hopefully everybody agrees with me. This is a reasonable implicit version of a sphere. In fact, it would be kind of annoying to come up with the explicit, like a parametrization of the sphere surface. Any questions so far? You guys are like rolling your eyes like it's easy, but I promise you it'll get much more annoying next time. This is our break. Okay, so once again, we have a similar problem, right? We have array P of t, which is equal to r naught plus t times r d, right? There's our, maybe our naught and our r d. It runs into the sphere and it hits it at some point. And our goal is to figure out where that point is. How should I do that? I'll give you a hint. It's the same as how I should solve the other problem. Oh, wait. Put me out of my misery. Oh, now we're playing chicken, huh?
Plug it in.
Thank you. We can plug in this expression into the thing on the top and solve for t. Cool. Everybody's awfully quiet. If you're not following, you should speak up. It's okay. It's why you're here. Okay, so let's plug in this expression. What am I going to get? I'll get r naught plus t times rd. I want the norm of that squared, which is like the dot product with itself, right? So that's minus r, like that. And our goal is to solve for t, right? Everything else here is a constant. You see that? Okay. So unfortunately for us, we have to do a little bit of algebra and actually expand this expression, right? So I'm going to move the 0 onto the left-hand side. Okay. So what should we do? I see a product, so we should, FOIL it, right? We should multiply everything out. So we get r0 dot product itself, which is the norm of r0 squared, plus t rd r0, t rd r0. Remember that dot products are commutative, so I can do that. Plus t squared times the norm of rd. Like that. Okay, did I manage to expand the product right? I think I did. Okay. So that's to solve for t. This feels complicated, but it's really not so bad. So in particular, let me write it in a kind of suggestive way here. So we have, this is t squared times rd squared. I really struggle to write on the bottom part of a board. Plus t, and then what do we have here? We have 2 rd dot r naught. Plus, and then basically everything else, right? Plus r naught squared minus r squared, like that. Have I managed to do it right? I think I have. Okay. So let's give these three things names. Let's call this quantity here A, this quantity here B, and this quantity here C. Yeah? And notice that these are just functions. Like, these are just constants, right? Like, they're defining the sphere and the ray. Right? This doesn't have anything to do with our unknown variable. Right, so what is this expression equal to? Well, in my notation, it's at squared plus bt plus c. Ugh. This is one of relatively few lectures in this course, so it would be kind of nice to use both sides, but I know there's YouTube people. Okay, so what were we doing? Well, our goal is to solve for t. We've written a, b, and c as basically constants in terms of our problem. What are we going to do? I see you nodding. No. What's that? The quadratic equation. That's absolutely right. Yeah, so we all know how to solve quadratic formulas for t here. So, what is t? Everybody all at once. Yeah. So it's negative b plus or minus the square root of b squared minus 4ac divided by 2a. Yeah. Right. So notice that there's something a little fishy here, which is this plus or minus. Okay. So those are all the places that our line runs into our sphere. Cool? All right. Notice that this is something I can code, right? Like a, b, and c are just functions of parameters, and now I just plug into this formula. From a numerical analysis perspective, it turns out that there are actually better ways to implement quadratic equation, but we're not going to worry about that a whole lot in this class. Okay. So right. So here's our our equation. I think we managed to do it right. And here's our formula for ray-sphere intersection. So now notice that there's kind of an interesting thing. We have this value here. What is this thing called? At least the thing inside of the square root? Discriminant, right? So let's label d as b squared minus 4ac. And now, you know, this is just high school algebra. I see a lot of like, you know, laptops and the phones are coming back out. But I do think it's worth thinking about, you know, if I'm doing my ray-sphere intersection, like what is my discriminant actually telling me about my ray tracing problem, right? That's a really important thing. So first, let's think about d is less than 0. So when the discriminant is negative, how many solutions does my problem have? How many solutions are there? 0, right? There are none. I can't take the square root of a negative number. We're not doing like crazy imaginary rendering. What does that correspond to in ray tracing? This is the critical thing. Like, get some intuition here. Like, what is negative d? Yeah, here's my sphere. Here's my ray. Yeah? All right. How about d equals 0? Intersect one time. What does that mean about my ray? It is tangent to the sphere. Like that. And when d is greater than 0, well, then it goes through the sphere. Right? So that's the picture to have in mind. Obviously, these two cases are easy enough to detect and deal with. This third one is mildly annoying, right? Because there are two different t's, right? Like, essentially, I could put plus or minus this value here and get two different intersection points, and that's perfectly valid. Yeah? So which one should I choose? The smallest one. Yeah, so you've all walked into the trap except for Maxime here. So what's our gotcha here? That's right. So you get two different values of t here, and you want the smaller of the values that is positive. Right? So like if one of these is -1 and the other is +1, then I should take the positive value. Right? So a mistake in your code would be to just use that minus sign. Does that make sense to everybody?
So would we just assume for the cases where we're inside the sphere? Basically?
That's absolutely right. Yeah. So if I think of my ray direction maybe as like this way, right? Then here are three cases, right? One is here, one is here, one is there, right? So if I'm here, there are two positive t's, and I should take the smaller one. If I'm here, there's one positive and one negative, and if there's here, there's two negative, and I don't actually intersect at all. Make sense? Yes?
Like glass though, like does that make a difference, or does that glass, is that kind of like a shading thing that comes after?
Yeah, so we haven't talked about material. If the sphere is glass, then yeah, you've got to cope with both intersections possibly. We're going to deal with that by thinking about what happens when you intersect that first point. Like, what should happen to the ray? Should it go through? Should it bounce? Should I just do diffuse lighting? So we're going to talk about that later. Any other questions? Cool. All right, so those are our three cases. We have to choose them very carefully. This is the smallest positive value. Once again, once I've chosen my t, I can plug it back into my p of t to actually get that intersection point, which is going to be needed, for example, if I want to do that lighting calculation. Okay, so there it is, and now you can render exciting scenes like spheres and checkerboards. So we're getting there. Of course, for shading, we need one additional piece of information, which is the normal to the sphere at the intersection location. How could I get that? I think we probably all have the right intuition, but it's a little tricky to articulate. Like what mathematical formula should I use? So I have the location of the intersection. That's fair game because I just told you how to compute it. I also have the center of the sphere. So what should I do? The difference of those two, right? Like you can see if I have q minus o, that's a vector that points out of the sphere, and that's exactly the normal vector. Okay. You might want to divide it by its norm, of course, if you want the unit normal. I think it's pretty typical. All right. And so, again, you know, I can keep showing you all these ray tracer test images. There are many of them out there. Essentially, people got very excited in the 80s and rendered lots of spheres attached to more spheres because those were the things we knew how to ray trace. I think this is some, I don't think it's quite Mandelbrot, but it is some fractal or another that somebody's managed to engineer. I doubt that they did it in the right way, like actually working out the ray sphere intersection for the limit surface. But what do I know? Okay. So as a quick recap for today's lecture, I think this is one of the sort of easier ones. This is sort of using basically the pre-calculus math that we've done before. What are the key points here? I think we now know roughly the sort of image formation process and specifically the pinhole camera model. And beyond that, we talked about the basics of ray casting, which include creating the rays and then intersecting them with spheres and planes. Next time, we're going to talk about barycentric coordinates and specifically how to intersect a ray with a triangle. What's going to be the headache? So remember that, what triangle meshes have you guys worked with so far? I think you had the teapot and bunny, a few other things. And just those meshes, which are pretty simple ones for your homework, had, what, a few thousand triangles in them? So what does that mean for that ray tracing algorithm? Remember, we have two loops, right? One is over pixels and one's over every single object in your scene. Yeah, well, I don't know if I'd say n squared, but it's like the product of the number of pixels and the number of triangles, right? Every single pixel has to iterate over every triangle to figure out what to light up. And then now you can see why this is such an expensive algorithm to implement the way that we've given it today, right? Even a simple object, if it's comprised of many triangles, yeah, this calculation is easy, but you're going to multiply it by 10,000 to render a single center of one pixel. So one of the really critical things we're going to talk about in the next couple of lectures is how to take this algorithm and accelerate it. And of course, there are many ways to do that. There are some interesting data structures that we're going to use. So with that, I'll see you next time. Really, get started on your homework if you haven't already. This is one of the trickier ones. And next time, we'll keep talking about triangles. And I hope the recording actually worked. I'm sorry for rushing in at the last minute. Okay.